Hello, and welcome back to Shiksha Costa. Today we're going to be comparing experimental and theoretical probabilities in our unit on applying probability. So today we're going to learn what is the relationship between what we learned in our previous lesson, experimental probability, and what we learned the lesson before that, which is theoretical probability. And you're successful at these skills when you can compare through some sort of investigation compare the theoretical probability and the experimental probability of an event and explain why those two might be different. And also when you can determine through an investigation using some sort of technology-based simulation model, so you won't actually be doing the probability experiment yourself, you'll use some sort of technology to simulate the experiment. And using that, can you determine that the experimental probability is going to approach theoretical probability or not as you increase the number of trials? So we'll see both of these things happen in this experience. So in our previous investigation, we obtained the following data set. Okay, but it took a long time to calculate. Remember, we rolled 10 dice once. Like 3D4, we rolled it 10 times. We recorded all of our rolls, and then we found out, hey, what percent of my rolls fell under each number? And in this, when we just did 10 rolls, we noticed that, okay, we have 3 eighths, 3 out of 10 is 30%. And then we rolled it another 10 times, and now we looked at all of these. And we realized that, okay, now there's only 20% of these are eighths. There's 1, 2, 3, 4. 4 out of 20 is 20%. And then we kept going until we had done 100 rolls in total. And now we see the experimental probabilities have changed. 12%, a roll of 12 happened at the start. So 1 out of 10 is 10% of our rolls were 12. But notice that as we did more and more rolls, we saw that, hey, only one other 12 ever showed up. Right? It was very hard for us to actually roll a 12. And therefore, 12 did not make up a very large percentage of our rolls by the end, just 2%. But now let's compare these results to the theoretical probability of rolling 3D4. So this will take us back to 2 lessons ago, where we looked at the theoretical probability of rolling 3 four-sided dice. We said, okay, the first dice can be a 1, a 2, or a 3, or a 4. And for each different number, for each different outcome, there are 4 outcomes that come from that, which is the purple dice. And that could be a 1, a 2, or a 3, or a 4. So in total, right now, there are 16 outcomes. But for each of those, there are 4 outcomes for the red dice. And 16 times 4 gives us a total of 64 outcomes. The lowest we could roll is a 1, 1, 1 for a total of 3. And the highest is 4, 4, 4 for a total of 12. And we looked at the frequency of how often these numbers pop up. There's only one way to roll a 3, but there were 3 ways to roll a 4. Right? There's a 4, you can get a 4 by rolling a 1, 1, 2, a 1, 2, 1, or a 2, 1, 1. There are 6 ways of rolling a 5. There are 10 ways of rolling a 6. 12 ways of rolling a 7. 12 ways of rolling an 8. 10 ways of rolling a 9. 6 ways of rolling a 10. 3 ways of rolling an 11. And just 1 way to roll a 12. So we said, okay, if these are all of the different outcomes, this is how often they pop up. What is all of that as a fraction? What is the probability that I will get a 3 as a fraction? 1 out of 64. The probability that I'll get a 4 is 3 out of 64. And I can keep going with all of these. All of them have the same total number of outcomes, so I'll just divide the frequency by the total number of outcomes, and therefore I'll be dividing all of them by 64. How do I convert that to a decimal? Easy, I just divide these two. So if I divide all of these to get the decimal versions, these are all the decimals that I get. And finally, I'll want to convert those to a percentage. And so I'll just multiply them by 100 to get the percentage. So this right here is the theoretical probability of getting each of these numbers when rolling 3d4. The question was, how does this compare to our experimental probability? So just going back to that experimental probability, I'm going to import my frequency table, and I'm going to put those results as well on the bottom here, right? This is the theoretical probability, and these are the experimental probabilities. And I'll ask you this question right now. You can pause this for just a few minutes to examine this chart, and I'm going to ask you this question. What do you notice is happening? So hopefully you got a chance to look at this data, and whatever you notice, big or small, is valuable. You may have noticed stuff like, hey, the theoretical distribution forms sort of like a hill, like the central values between 6 and 9, those are the highest numbers, and then the further out you get, the lower the probabilities get. You may have noticed that 11 and 12 seem to have the same probability, except once we start getting towards 90 and 100 rolls. Until then, they had very similar probabilities. You may have noticed that even with 10 rolls, the middle numbers seemed very high, although with 10 rolls, it seems a little bit more chaotic over here. And I think what would really help is if we had column charts. It's really tough to look at numbers and then you have to make a mental connection between the number and sort of what it might represent. So let's look at a visual representation of all of these. So this is the, when we did 10 rolls, this is what the column chart would look like. Now keep in mind that in colors back here, that is the theoretical distribution. But the black columns are actually the experimental probability when we did 10 rolls. Notice that 8 is at 30%, 6 and 7 are at 20%, 3, 4, and 5 are at 0%. They're all the way at the bottom here. Why would these actually be different? Why would the experimental probability be different than the theoretical probability? You can pause the video here and really think about that and see if you can come up with a solid answer. So you might say to yourself, okay, even though we guessed that these were the outcomes that would happen, when you actually roll the dice, there's never any way to be sure exactly what is going to happen, because the dice kind of do whatever they want. In fact, theoretically, there is a chance, it's a very, very small chance, but there is a chance that with all 10 of our rolls, we kept on rolling a 12. That chance is so small that I would say it's really, really, almost impossible to roll a 12 10 times. You would have to beat this, 2% probability. And you have to do that 10 times? That'd be crazy. But it is possible, right? Dice sort of just do whatever they want. So that is the reason why experimental probability is different from theoretical probability. Even though we might predict the probability of something, when we actually try it out, who knows what is going to actually happen. But now let's look at what happens when we increase the number of rolls. So this is with 20 rolls. Notice that the probabilities, the probability of rolling an 8 has decreased dramatically. And the probability of rolling a 5 has jumped up from 0 to 15%. Now this shape, it still isn't a normal distribution, right? We can see that it goes up and then it goes down and then up and then down. So it's almost like it's bimodal. But it's looking a little bit more like a normal distribution, isn't it? This is with 30 rolls. This is the experimental probability with 30 rolls. This is it with 40 rolls. We can see the 8 started to pop up more and more often now. If we roll it 10 more times, this is what I get. That's 50 rolls. $60 rolls. $70 rolls. $80 rolls. $90 rolls. And finally, 100 rolls. This is the experimental probability of rolling 3D4 100 times. What did you notice was happening? One thing that would have been really sort of immediately obvious is that as we increase the number of rolls, the lower numbers and the higher numbers, like to the left and right, they seem to get, the black bars seem to get nice and small, whereas the bars in the middle are nice and tall. In fact, it started to form more and more of a normal distribution, didn't it? And in fact, the theoretical distribution is also a normal distribution. So what could we say happens when we run an experimental probability, a probability experiment, more and more and more times? How does our experimental probability start to compare to our theoretical probability? What would we say about that? The more you roll, the more the probability starts to look like what you guessed in the first place, the theoretical probability. Okay? So let's do a quick investigation here. Okay, so we can actually run this experiment we did it for 100 trials, but we can actually run it more and more often. We can run it 1,000,000 times really, really easily if we don't actually try to roll the dice ourselves, and instead we use spreadsheets. So the function in a spreadsheet, when you use formulas in spreadsheets, you put in a formula, you put in the arguments, which are things you put inside the brackets, and it gives you an output. This formula, it's called rand between, and then you put brackets and you put two numbers here separated by a comma. This will generate a random number between x and y, which is the same thing as rolling a dice. For example, if we wanted to simulate rolling a D4, we would use the formula equals rand between 1 and 4. So this is what that might look like. If I opened up Google Sheets or Microsoft Excel and I started with any cell and I put equals rand between 1 and 4. Notice that it's giving me some help here. It's saying, hey, this is an example of this is the rand between, then you put a low number, then a high number. This is an example, for example, 1 and 10. What does this formula do? It returns a uniformly random integer between these two values, including those two values. So a random integer between 1 and 10. What do you put in for low? The low end of the random range. What do you put in for high? The high end of the random range. And then it gives you an example of what it's going to output. It calculates it for you. It says, okay, a random number between 1 and 4. Okay, I'll give you 3. But this could be any number from 1 to 4. To simulate 3D4, we would actually need to generate 3 random numbers and then add them together. So my formula might look something like, so you might be tempted to say, oh, 3 4-sided dice, that's the same thing. Like the minimum I would get is a 3, 1, 1, 1 equals 3. Or if there were 3 4-sided dice, I could get 4, on all 3 of the dice, and 4 times 3 is 12. So maybe I'll randomly generate a number between 3 and 12. But that would be a mistake because you're not rolling a 12-sided dice. Each of the numbers is not equally likely to come up when you roll 3d4. Remember, a 7 is much more likely to come up than a 12. And so we have to consider that as well. So our formula would look something like this. Rand between 1 and 4. This is one of the d4s. Plus rand between 1 and 4. This is the second dice, or the second die, excuse me. Plus rand between 1 and 4. This is the third die. These are 3 dice. I've generated 3 different random numbers, and now I'm adding them together. So what we're going to do is we're going to enter this formula in cell A1. So this is going to be a roll of 3d4. And then I'll copy this formula and I'll paste it to all of the cells from cell A1 to cell A1 million. And I can do this really easily just by clicking this little circle, or sometimes it's a square, clicking it and dragging it down, and you notice that it's filling out all of these with the same formula. Okay, I don't have to copy and paste it. I can just click on that circle and I can drag it down just like this. So clicking on it, I'm dragging it down, and then when I release, it will copy my formula to all of these cells. And now we've got our roll data. We've done this 1 million times. And now we can use another function that I'm going to teach you called COUNTIF. And that will count all of the outcomes, and it'll count how many of each outcome occurred. And I'm going to show you how to do that. So this formula will help us avoid having to make a frequency table, because now that we have 1 million rolls, do you want to be the guy that goes through all 1 million rolls and counts how many 3s there are, how many 4s there are? Like, no. We're going to use the computer to do this for us. So COUNTIF, and there's, again, 2 things you need to put in here, a range and a criteria. This counts the number of occurrences that match your criteria within the range that you specify, and a range is a number of cells. So this is how it looks. For example, COUNTIF A1 to A10, and then the criterion is greater than 20. So this is going to return a conditional count across a range. So it's going to count how many of the cells from A1 to A10 have a value that is greater than 20. So my formula is going to be something like this. COUNTIF A1 to A1 million, and then the criterion is 3. This will count the number of 3s, and let me just highlight that for us, the number of 3s within my range. And let me just highlight that in orange. The range is A1 to A1 million. So column A from row 1 to row 1 million. It's going to look at all of those cells, and it's going to count how many 3s are there. So this is what my spreadsheet will end up actually looking like. Here I've got all of my roll data from A1 to A1 million. And then I've got a formula in here, and notice my formula is slightly different, and I'm going to show you why that is. My formula is actually COUNTIF A:(A), that's my range, and because I didn't specify any numbers, it's going to count the whole column from A1 to A infinity if there are an infinite number of cells. Now I only have 1 million cells, so that's okay. I just wanted my formula to look a little bit cuter, a little bit smaller. So A to A, this is counting all the cells in column A that have this criterion. What does C3 mean? Well, remember, in spreadsheets, there are columns, A, B, C, D, E, F, and there are rows that have a number. So C3 is the cell, column C, row 3. Do you notice it's highlighted in purple here as well? So the spreadsheet will help you figure out exactly which cell you're talking about. So this formula will count all the cells in column A that have the same value as cell C3. And notice what's in cell C3? The value 3. So it's going to count all the 3's from column A. And then again, I can do that click and drag the corner all the way down to fill out the entire table. Now, I've made this table myself, right? I've put in the roll data. I've put in my theoretical probabilities. Now I'm putting the frequency, and to actually count the frequency, I'm using the COUNTIF formula. So I drag that corner down here, and notice that as I'm doing it, this cell, C3, it automatically changes. If I had that in cell E3, yes, it was referring to C3. But now if I have it in cell E12, now I'm counting the number of 12s, because in C12 is the number 12. That's my criterion now. So just like this, it has automatically counted every single 3, every single 4, every single 7, every single 10, and it's put the total number of times that those have appeared in this range right here. So this spreadsheet will help us with the frequency. I have put in myself the theoretical probability, but what about the experimental probability? Well, spreadsheets can also do math for us. They can do arithmetic, adding, subtracting, multiplying, dividing, all sorts of stuff. So in fact, for experimental probability, I'm just going to divide. Remember, I have to divide the number of successful trials. So that is in cell E3, I'm going to divide it by 1 million, because that's the number of rolls. 1 million total trials. And in 15,623 of them, I rolled a 3. So that number, 15,623, divided by 1 million, it's telling me what my answer will be. It'll be 1.5625%. And I'll just I'll do the same thing where I drag the corner. I click and drag the corner to fill out my entire table, and that's how I got all of these percentages. What do you notice, if you're able to zoom in at all, what do you notice when we compare the experimental probability to the theoretical probability when we have done 1 million rolls? One of the things I noticed was that when we did 1 million trials, the experimental probability became almost exactly the same as my theoretical probability. They're not exactly the same. Notice this is 1.5623%, and the theoretical probability was 1.5625%. So it's slightly off. And that's what our lesson for today is really all about. The more trials an experiment has, the more reliable its data is. And as we observed, the theoretical probability is the most accurate predictor. And the more trials we do, the more the experimental probability itself approaches the theoretical probability. The closer and closer it gets to being the same thing as the theoretical probability. We also learned about the rand between function on spreadsheets. You can use this function to simulate rolling dice. And we can use the COUNTIF function to help us create frequency tables when we're doing like 1 million different trials. And I've got a QR code here where you can try it out for yourself, where you can go to a spreadsheet, you can try out these dice rolls. I have a few examples of the rand between and the COUNTIF functions for you to go ahead and try out there. So if you'd like, you can definitely go ahead and do that. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.